Okay, so more in spanning trees, Prim's algorithms, and backtracking. So if you have a weighted graph like this one, where every vertex has got a weight, Prim's algorithm, which is what the math department, not the math department, which is what the book calls algorithm 9.4.3, is what's called a greedy algorithm. And it is guaranteed to give you the spanning tree of minimum weight. The algorithm is very simple. You start somewhere and you add the least weight edge you can at every step. When you've got all the vertices, stop. Unlike the traveling salesman problem, this one actually does guarantee that you get the best possible outcome. The traveling salesman problem doesn't. So what's the least weight spanning tree for this graph? Like most spanning tree algorithms, you have a live vertex, where you are in the graph, and then you have options. Right, so suppose we want to start at A. So A is live. What are the options from A? You can go to B, that costs you 4 units, or you can go to D, that costs you 12 units. So out of all your options, what do you do? Well, this is the least weight one. So you go to B. I'll start drawing my tree here. A is here, B is here. That's got a weight of 4. Great. From B, what are the options? You can go from E, but that costs you 6. You can go to F, that costs you 7. Or you can go to C, that costs you 1. We did that option. So where do you go? And note we don't list A here because we've already been to A. So C costs you 1. So from B, you go to C. And that costs you 1. Right? And so for building up our spanning tree, we started at A, we went to B. From B, we went to C. Great. So we've done A, we've done B, we've done C. At this point, we have a bunch of different options. Oh, C is now live because that's the last one we added. And from there, we can get to F at a cost of 5. So now we have a bunch of different options. We've got D is 12, C we've done, E is 6, F is 7, F of 5. This is the cheapest. So we join that one to our list. We go to F for weight of 5. So there's our graph building up, our tree building up. Once we're at F, what are the other possibilities? From F, you can go to E. That's a weight of 14. From F, you can go to I. That's a weight of 9. So all of these are live. You can consider whichever one you want to go to, but F is no longer an option because we've been there. So of the options that are available, which one's the cheapest? Going to E from B costs us 6. That means we add this to our tree. And as we're drawing the tree, we say, okay, E, that costs us 6. So there's our tree. So we add E to our list of live vertices. And what are the possible places to go from E? You can go to D, that's 11. You can go to H, that's 3. Or you can go back to F for 14. Of course, you can't really go back to F because F is already on the graph, so we don't want that. E is on the graph means this option is no longer available. So out of all the options available, what do we have? 12, 9, 11, 3. That's the cheapest one. So H becomes our new live vertex. That comes off of E for a count of 3. So it goes down there. What's available from F? From H? I, and that counts 10, and G, and that counts 2. Oh, and D also, and that counts 13. So we've done this one. Any H's have to be crossed off because they're not allowed. Okay. What's the cheapest one left? Well, we look through that. 12, 9, 11, 10, 2, 13. That's the cheapest one. So G off of H counts 2. So there's our graph building up. G off of H, that counts for 2, and that gives me this. And what do we have also from G? Well, G gives me a connection to D, which is 8. And so what do I have left? Well, D12, I9, D11, I10, D13, D8. That's the cheapest. Where's my red pen gone? There it is. So off of G, D, that's 8 units. So now D is on our graph. And what's left is I. What's the cheapest way to get to I? 9 from F. There's F. So there's our tree. And there's a tree built up like that. So what's it cost? Least weight tree, 5, 10, 19, 25, 28, 30, 38. So how do you go about doing that? Start somewhere, list what your options are, take the cheapest option, add where you go to the list of live options, list whatever options you look at the collection of options, take the cheapest one, add that on, add its options, look at the collection of options, take the cheapest one. So a search tree is a way to look through possibilities. A classic example is the 4-queen problem from chess. The 4-queen problem is like this. We'll look at a very small chessboard with only 16 squares on it. A queen, if you put her on the squares, can attack anything on the same column, anything in the same diagonal, and anything in the same row. And the question about the 4-queen problem is, can you get 4 queens onto that 4x4 chessboard so that none of the queens are attacking each other? So how do we solve this? Well, you start with an empty 4x4 chessboard. And then you pick one place to put your first queen, right? So the idea here is that we want to build up an algorithm to be able to solve these sorts of problems that have sort of these repeated choices. So we say, okay, we'll tell the computer you pick always the first available space in the first column, then you go to the second column, you look for the first available space going down that column, et cetera, et cetera. So it starts by putting a queen up in the first 1, 2, 3, 1, 2, 3 space. And then you say, okay, computer, now tell me where is the place to put it in the second. And it'll say, well, I can't put one here, can't put one here, but I can put one here. So it says, okay, I can put in 2 queens, one here, and those are not attacking each other. Where can I put one in the third space? I can't put one here because of this queen. I can't put one in any of these because this queen attacks them all. So terminated, doesn't work, unhappy face. So how do we deal with this? You go back to the last time you had an option. So we go back to here. It says, okay, we know that putting it here doesn't work, but we could have put it there. So that's the backtracking part of this. Backtrack to the last place you had an option. Could put it there, right? Now can I put one in the third column? Sure, I can put one not here because it's attacked with there, but this one's not under attack by either of the other queens. So I can put 1, 2, 3, 1, 2, 3, queen here, queen here, queen here. Where can I put one in the fourth column? Well, I can't. This is attacked by this one. This one's attacked by that. So that terminated. Didn't work. So we go back to the last place we had a choice. Where's the last place we had a choice? Didn't have a choice here, right? Once you put a queen there, this is the only option. Go back to here where we checked this one and this one. So there's no other options in the second column. So the last place we had a choice was actually up here. Instead of putting a queen in the first, in this square, let's try putting one in that square. So suppose we put a queen there. Well, where can we put the next queen. You can't put one here, 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 but you can put one down there in the bottom there. 1, 2, 3, 1, 2, 3, queen there and a queen there. Can we put a queen in the third column? Sure. These three spaces you can't use, but this one you can because it's not under attack by any of the queens. So I can put a queen here, and a queen here. Can I put a queen in a fourth column? Yep. Oh, not there, here. Can I put a queen in the fourth column? I should be able to. Nope, that was right. Sorry. My drawing. 1, 2, 3, 1, 2, 3. This queen is here, this queen is here. Now I can put a queen up there. And then finally, I have a queen here and a queen here and a queen here. Can I put one in the fourth column? Yes. That worked. So looking at the structure of this, zoom out. Right? It's a tree. Here's the root. We went down here, that didn't work. We went down here, that didn't work. We went down here, that worked. So we can stop. If this hadn't worked, you can imagine putting the queen in a different place and running through the search tree. There's a lot of different possibilities because you have 16 different places to put the first queen. And so a search tree is this sort of thing, right? You start with one place and you just try out various possibilities until you get to something that works. You don't actually have to search the entire tree. So you can do this for Sudoku. If you've ever played Sudoku, you can write a program that would solve these sorts of things. So here's a Sudoku picture that I found somewhere on the net. How do you want to solve this? Well, you start by looking at this square and saying, well, what numbers can I put in there? Can't put in a 3 or a 5, a 1 or an 8, 1, 5, 4, 9, 3. So you can put in a 2, right? A 2 is the least number that you can put in there. So if you put a 2 in here, then what can you put in there? Well, you can't put in a 1, a 2, a 3, a 4, a 5, or a 9. So the 6, 7, or 8 are possible. 8 is possible, 9 is possible. So 6 is the least. And you fill that up, right? What's the other number that can go in here? That must be a 7 because that'll give you all 9 numbers there. So then you go up here and see what number can fill that in. And you just keep going. And every time you hit a problem, you backtrack to the last place you had a choice, make a different choice, and then resume. And keep doing that. Then eventually you fill out the whole thing. So search trees are a very useful way to grind through these sorts of problems.